Well, this is just abstract. These are the people who actually helped me on this big project. Mostly with the Honendo. It's the joint paper with the Honendo. But the underlying technology, some part of the technology I actually developed with the Haekyung former postdoc a while ago. So let me go over the
SARS-CoV-2 is the novel virus that causes the COVID-19 disease. The ACE2 receptor exists in abundance on the surface of lung cells and is a target for the SARS-CoV-2 virus. The spike proteins protruding from the virus attack ACE2 receptors to gain access to the interior of the human cell, where they can. Researchers are experimenting with new biologic drugs like human recombinant soluble ACE2, HRS ACE2. These decoy receptors attract and connect with the spike proteins, enveloping the virus and preventing it from connecting and entering with human cells.
So the COVID virus is basically like have this kind of spike sticking out of the virus. And this is one example. See this? It's about how many atoms? About 20,000 atoms. And it's basically 3 domains, 1 to 3. It's symmetric like this. It has a rotational symmetry. And so we're gonna actually look at this COVID-19 virus here. It's like a tetrahedron shape, and there are 2 states. One is closed, the other is open state. When it is open, it's much easier to attach the host cell. So almost all the vaccination effort has been preventing or disturbing this process actually. So I would say most of those purple vaccines, mostly like a Pfizer, does that actually. So my guess is that almost all the mutation is increasing this open state. I don't want to say most, but some of the mutation. So in that sense, I think the vaccination effort should be quite reasonably okay, even against the mutations. So we want to see if there's any topology changes in this closed state and open state. Well, it looks like there's some changing in the actually geometry. We need to know how close they are topologically, but we need to know in terms of property. Why? Suppose you compute the Wasserstein distance between these two objects. What does it even mean? Does it have any meaning? Unless you have some sort of reference distance. So, you know, if you have a reference distance, you can establish some sort of probability statement, how close they are in terms of the percentage or probability measure. So that's what I want to do. And we basically want to compute the p-value. And so now this is something I've seen in a lot of the TDA literature. Simply comparing the mean value doesn't mean anything actually. I'm saying this because I've seen it so many times. Suppose you have three measurement. I want to compare. Eh? So I said that the mean of these three numbers are bigger. It's 4, while it's 3. So this must be different from this object or something bigger. That's the fallacy. That's incorrect, logically incorrect, mathematically incorrect, statistically incorrect. Now, this argument only correct 50% of time. What does it mean? It's the same as the flipping coin. You can say anything you wanted purely based on the measurement, average measures. Now, this is a demonstration. Suppose I'm going to generate the random numbers from 0 to 1, 100 times, and put it into vector A and put it into vector B. And I'm going to count the number of the times. I'm going to basically subsample 5 numbers, and compute the average and average C, whether the average of the vector B that has been subsampled is bigger than this, and count it, and then compute the probability. then what we're gonna get is that this number 0.6, 0.5, 0.7, 0.48, 0.42, it's essentially a random number. So in that sense, it doesn't mean a thing. So what we have to do, what's missing here? The missing is, now, if you want to claim that you claim purely based on the comparing mean, your number of mean you are computing should be really based on a large sample. Suppose you have a 1 million measurement, then comparing mean may matters. It's meaningful. But simply comparing, I actually picked this example 3 because that's what I saw in the paper. 3 numbers, measurement average of 3 numbers. So it actually deals with the you need a large samples, also variability. Variability usually means the variability between the measurement. Then how do we do the inference on average differences? You can do average inference in average difference, but that has to be respect to some reference distribution. It's what we call the null distribution under the assumption of the equality. Then based on this null distribution, we have observation, which is basically the difference of the mean factors. We observe it, see where this belonging to. If this is somewhere here, then we cannot conclude anything. If this is away from the center and close to the extreme values, then we're gonna see that, oh, that's a very rare event. Rare event usually don't happen in practice, so that's a signal. That's how you do the proper statistical inference. So this is topology inference is basically my main research area. Even though I do a lot of topology, my focus is only mainly on the probability computation, basically, or inference. So how do I get into this area? Actually, I got into this area with through Peter Bubenik and Peter Kim. I usually call them two Peters, actually. And it's my first paper in 2009. And I learned that all the Partial homology I need to know from Peter Kim. So he was my teacher, more like my mentor on a TDA aspect. And this is actually the first paper actually that smoothed the Partial diagram. You see these days, everybody smoothed it. It's the idea actually came from this paper. So what we did was that we have this kind of the data coming from the brain surface. Then we have the Partial diagrams. Then always basically have to do the static analysis. I thought about this doing a support factor machine because we have this kind of the y and x kind of the slope. But that's nonsense. If you apply the most of the machine learning method, it will not work because there's too much overlap between the two groups. In the imaging field, there's a saying, if you're stuck, smooth the images. That solve a lot of problem. So that's what I did. I actually smoothed the images. In this case, we used the uniform kernel. That means it's a counting measure. And basically, we performed the two-sample t-test across the multiple data. So it was actually the first, I think it might be the first paper doing a proper statistical inference on a Partial diagram. But it's a nonsense. I want to say this is nonsense, biological nonsense. I'm actually more strongly about this, even though our group was supposed to propose the smoothing Partial diagram. Now I'm going to discount it. Why? Now think about it. This data here, scatter point might coming from two different brain regions here. So if you smooth it, we are essentially contaminating signal here to the signal here. I'm sure that they give you same topology, but that's not usually the people want it. They want to do the back projection. Most of the brain imaging people want to not only look at the global differences, which TDA gives, but we also want to look at the local signal differences. And the smoothing this doesn't give this kind of the localized information. So question is, how are we gonna do the data analysis, static analysis without smoothing Gaussian diagram? Or well, this is example of the Lips filtration actually on the COVID-19 virus. It's a closed state and open state, and this is the COVID virus of the cat actually. So it's not human. If you look at it, that looks quite similar. Now, suppose you smooth it. Suppose you smooth them, and then they look almost similar. So if smoothing the Gaussian diagram will not give you those fine detail. So I just want to give you some motivation. So what we did was that we're going to define from Gaussian diagram, we're going to basically define the process, stochastic process. We're going to call it the both and that process. So C1 up to C2Q. You see this subscript and this bracket. It's called the order notation, coming from the statistics. Actually, it's a proper mathematical notation indicating the ordering. So I'm going to order the both and that. I'm going to combine them and sort them. Then one of those will be both or that actually. So we have this. We're going to assume that. Then we're going to identify both as the arrow, 45 angle arrow, that as a 45-degree angle arrow. Then just follow the arrows. So both, that, both, that. Okay? So I'm going to form a pattern with the path, and this path has a name. It's a dark path. This is widely studied in a combinatorial basically, but still this is very hard. People are still trying to compute things. I noticed it. It's not easy object actually. So the path start from 0 and 0, and it end then the square root of 2q0. And then path always, nice thing about this path is that it always should stay above. It cannot go down below the horizontal path. Then why this matters? This is quite, if you look at it, you can see that this actual form of path is a single path. So other Gaussian diagram can be represented as another dark path. That means I can form up the sample space, collection of the dark path that form a sample space and assign the probability for each dark path, then build a probabilistic model. Okay? So this is 14 possible dark path for Q equal 4 here. This is the only possibility. So what would be the total number of dark path? It's what they call Catalan number. That's exactly given by there. If you go to Wikipedia, you can actually find out about 10 different proof for this. And then how you quantify the dark path. So I thought about this. So I thought we can do this by area below the dark path. Now, if you have a but that like this, we have a very big, large persistence here. Now, if you look at these cases, it's fluctuating. But and that usually means it's a high frequency noise with a small persistence. That means area below this dark path is very low, small, compared to the large area here. So if you're interested in the problem, I recommend you prove this statement more rigorously. I'm sure you can do it. You just need to identify relationship between the area differences with the Gaussian diagram differences, basically based on a distance measure. So in terms of mathematical difficulty, I don't think it's that complicated problem. So what's the area under the dark path? Well, look at the area under the dark path. Now I'm going to rotate this by 45 degree, rotate this and flip it. Then what do I get? This is called the lattice path, and this one has to be always monotone. And just like dark path, this lattice path cannot cross y equal x axis. Because you cannot have more depth than the bird. So y cannot be bigger than the x-axis. So that gives you some constraint. Then area below dark path is equal to half the square subtract by the area below the lattice path. So area below the dark path, forget it. I'm going to just analyze the area below the lattice path because that's equivalent. And we have a 14 possible lattice path. Now, this nice thing about this lattice path is that it's increasing from 0, 0 to QQ in increasing fashion. So it's called the monotone lattice path. And nice thing about the combinatorics is that all these math people worked out a lot of the tools, computing, enumerating, and by the way, this is not a vector space. Right? As you can see, it's not a vector space because you can define addition here, addition of the two monotone lattice path, but you cannot define a subtraction in a meaningful way unless you do some sort of the additional constraint. If you look at this, the area below the lattice path, I mean, this lattice path itself is also increasing monotonically. At the same time, the area, see this, the gray square, this area is also increasing. So in this case, area is 0, 0, 0, 0. In this case, 0, 0, 0, 1, 0, 0, 0, 2. So this area below the lattice path is also monotone. That's very strong statement. Now we are getting somewhere. Now from this very crazy Gaussian diagram that doesn't show any pattern, we are having a pattern here. With this monotone pattern, we can build something quite nice. So this is an example of how we're gonna convert Gaussian diagram to the dark path, from dark path to the lattice path. Now I'm gonna represent the area below the lattice path as integer values. Then my Gaussian diagram can be represented into this number of sequences, integers. Why this matters? You can just feed these numbers into machine learning methodology. How are you gonna feed the Gaussian diagram itself into the deep learning? But you can feed these numbers into machine learning methodology without much effort and just learn it. See the simplicity of the idea? So we can do the learning, inference, and a lot of things. Then what's the limitation? Every method has a limitation. Every representation has a limitation. Then the problem is that we ignore the actual filtration values. We only worried about whether it's a bot or that and ordering. So this representation encodes the order information. It's basically encoding the one-dimensional information, one-dimensional topology information of the more complex topology process. And we are not actually encoding. Then how do you fix this problem? Well, I try to fix this to the dark path. See, instead of dark path, weighted dark path. I think I know how to do it. Just complicated. But if you do with a lattice path, it's much easier because it's humans. I think we worked on this lattice path or the rectangular grid system for since Greek time, more like 2,000 years. So everyone is familiar with this kind of the coordinate system compared to this kind of the very strange triangle shaped path. So what we do is that we just code the bot here and that value here and just trace it. That's it. Then instead of so then we also record the area here obvious area will be the difference between the both values and times the difference of the depth values. So it's weighted. Then if you encode this area, you should be able to recover the original Poisson diagram. Now, if you look at it, it is possible that we can have H2 and H3 identical. It is possible. It may be possible. Then, but we want to break this kind of the equality in such a way that we want to make the sequence of this areas strictly increasing, just for the mathematical convenience. So this is this gray dotted line is the areas, the product of areas, while the H prime is transformation, such that it's strictly increasing. How do you do that? You simply add little values. If you see this, simply add delta. If you see 3 sequences of the same numbers, you add the delta, 2 delta, 3 delta, etc., etc. So that's how you do delta, 2 delta. Then you construct. So I'm going to claim that this area will be, the area will be strictly increasing. Now, then what's the difference between H and H prime? I can make them as close to each other by making this delta to be extremely small. I can make a delta to be something like 0.00001. So we can just claim that in numerical convenience, that the area below the lattice path is strictly increasing in practical sense. Then we're going to put a step function pi. This pi will be between 0 to q. You will take integer values between interval 0 and 1. Now this is this construction is somewhat artificial. I'm trying to make some sort of cumulative distribution function, empirical cumulative distribution function that's actually needed. If you want to build Wasserstein distance on a discrete data point, you need this kind of construct. Same thing, same reasoning. So we have this. I basically form like this. Please remember that this value take integer values, nothing else. Monotone integer values. This is actually needed in the proof. Then this left side is lattice path for 3 structure here. 3 different spot here. Now, if you transform it, Q divided by Q, why Q? Q is basically number of the total number of both, which for each molecule. So by dividing by this, we are making this step function into 0 and 1. Exactly empirical cumulative distribution function. So this is how you do it. Now you can see that there are some differences. Now this one is so different because it's coming from cat, while these 2 spikes are coming from human. One is open, one is closed. So my guess is that that's why it looks so almost identical. The only change in that spike protein is that the little arm that's open and closed. That's causing these slight differences here. So we're gonna use a test statistic to be this. You can treat this as an empirical cumulative distribution function. Treat as this, so it can be viewed as a difference in an empirical cumulative distribution function. And in statistics, there's such concept. It's called the Kolmogorov-Smirnov the test statistical distance. It's invented by all these Russian probabilists, Kolmogorov. So we're going to use this. Now, what is this? Well, this is actually the upper bound of the area differences. So you see this, and if you take the area differences, This is actually the upper bound. So I'm going to use this upper bound as a test statistic and test the equivalence of these two processes. That's all you need. This is equivalent. This formulation is equivalent testing two Poisson diagrams. So instead of trying to compare the two Poisson diagram, I'm going to simply compare the sequence of numbers, which is a much easier problem. Eh? Do you agree? Comparing the sequence of numbers is much easier than comparing the Poisson diagram. It's not just a number, it's a monotone number, monotone sequence. So it's much easier. It has a structure. So we're gonna do this is very classical combinatorial argument. So we're gonna combine this two sequence, monotone sequence. We can do this under the null hypothesis, they're equivalent sequence. So we can simply combine them and then split them. Okay? Then they should be no differences. Then I'm gonna code it as arrow again. Arrow here, arrow, arrow, depending on where this number came from. So if this come from the first group, code it this way. It come from this here, code it this way. Then I'm gonna do the lattice path again, but this is a different lattice path. It's no longer monotone. It can go anywhere between 0 and 0 and Q and Q2. It's a number of the bud in the one group, and Q2 is a number of bud in the another group. And it's just then how many paths are there? It's Q1 plus Q2 choose Q1. This is a total number permutation in the two group setting. This number you cannot compare. If the numbers are bigger than 100 and 100, existing packages like Python or MATLAB cannot compare it. Number is too big to represent in the 16 digit or 32 digit decimal accuracy. It's too big, so you have to approximate it. This number usually in a computer is usually approximation, and the Stirling's formula is usually used. It's very accurate approximation, and it will give you exponential runtime. I mean exponential. That's how big the space of permutation is. And so that's why almost all the problems related to the permutation is NP hard. You cannot just compute it. It's just computationally, total number permutation is actually much bigger than the number of atoms in the whole universe. If this Q and Q2 is large enough. The space of permutation is much larger than the universe. You really have to understand that you have to get that into your body, and then I can put some property for each path. So I'm going to assign a property like this. Uniform property. Why? This is equally likely. This case is equally likely to another change of the permutation. So there's no preference. So this is a reasonable property assignment. Then I'm going to do then I'm going to basically do Then I'm going to find the property that this statistic is bigger than certain threshold. Why? Look at this statistic. If this statistic is bigger, that means there's this big gap. Sorry, there's a typo. It's not a DQ, it's D. Larger if this D is big, that usually means that there's a gap between these two monotone paths. That means that there are differences between the two Poisson diagrams. Now again, I didn't justify that. To me, it's obvious, but for some, it may not obvious. So you can actually justify. So if you're interested in this problem, I don't mind you taking over from my paper. But at least we did this. So we're gonna compute the property that this statistic is bigger than D under that assumption of this equal property. That's computable. even the permutation itself, you don't want to compute this with the traditional permutation test. That's brute force approach. Now, if you do this with our own version of combinatorial approaches for permutation, I can compute this exactly. Why? Accounting for every possible permutation. Well, that's the power of mathematics, the exactness. So you don't need to worry about the numerically doing it and worrying about the convergence issues like this. So what's the probability? Well, you just need to identify number of pathways. So the pathways A, U, V can be arrived here through this here and through this here. So only there are two pathways. So you can set up the iteration like this. Then the at the boundary is supposed to be 1, 1, 1, 1. That's only one possible pathways along the boundary. Now suppose you go here, then you have to go through here. Exactly. So you can actually set up this kind of the argument, and you can compute it. Now this is formula I didn't use for computing this. Well, you can work out you can write the method code where shouldn't be that hard. Probably my guess is about 10 lines of the code for computing this. Basically, you need to count the number of points within this grid. That's how now easiest way would be simply computing this part rather than computing this part. I don't know what would be the best strategy here, but at least that's the statement. The actual probability can be computed. Now this is exact. Now, but we are talking about the molecule. Even though it's mathematically exact, you cannot even compute this because it's like 10,000 here. 20,000 choose 10,000 is one. I'm sure it's something really big. So don't worry about those mathematical preciseness. Let's do asymptotics. And then you can show this, that this is very good asymptotic. Now, at least I did this for the Q is Q1 equal to Q2. Now, if you plot it, this is exact probability computation based on this formula. While the dotted line is asymptotic. Now you can see more or less like a very close. So if you use what they call the flow, the operation or ceiling operation, you can make this is exactly matched to all these corners. You can do it. And so it's now we are talking about the 10,000. So this is the Cryo-EM. It's basically new kind of the molecular imaging machine. Thermo Fisher Scientific is an American company, and it's from the Wisconsin-Madison. So if you want to do this, you need to come to Madison. yeah. So this is another machine. So inside of this is actually the electron microscope actually. The difference between the traditional electron microscope and this cryo is that the sample is frozen inside some sort of I actually give some sort of liquid actin actually, in such a way that you don't actually form a crystal. And so it's the structure seems to be like a very heterogeneous actually, and that seems to be giving us some trick to increasing the resolution. And actually people got the Nobel Prize. Now think about this is part of medical imaging scanner. Almost all the medical imaging scanner got the Nobel Prize. MRI scanner got Nobel Prize, PET scanner got Nobel Prize. So yeah, that's the medical imaging to me is the future direction for the big data science. So this is example. So 100 nanometer is something tiny. Right? You can see that this is this bar is the 100 nanometer. This is the virus actually. It seems like this tiny circle seems to be like a virus. Then you get this kind of the three-dimensional reconstruction of the molecular structure. While working on this, I never done this before, so I felt that actually doing topological data analysis on this molecular structure seems to be so not so cool. I mean, it's okay, but the more interesting scientific problem seems to be actually doing a reconstruction of this from the actual scanner. But that's not something we did actually. So we used the distance between atoms here and form a big gigantic distance matrix. Now I try to fit this into the couple of the packages because I don't want to do something called the graph filtration. If I do graph filtration, I don't have to use a package. I can do it immediately, but I want to does it the Lipsch complex and Lipsch filtration. So this is actually first time I had to do, and we use a Lipser, and because that seems to be the seems to be very popular now. So unfortunately, Lipser. Oh, I realized that since I never done this before, I didn't know how slow computation is. So doing this, I think it took me like a couple of hours in my computer, just getting the Lipsch filtration with the Lipser. That's not acceptable computation runtime in this area, in my area. My area requires scalable computation, very fast computation. Accuracy usually doesn't matter. We are doing a statistical analysis, so accuracy we can ignore. As long as we have many unbiased sample. But speed matters. So I was actually kind of disappointed actually. So this is how we get it. And that's how we compute the p-value. And how you interpret this p-value? Well, it's a product of the event occurring in the random chance alone as x seems small. Well, I think I don't know what how that this statement makes sense to you. I try to explain this in a very casual language rather than the statistical language. So this probability is very small. So random chance based on a null distribution, which is essentially coming from random distribution, essentially. So that means this probability is so small, it cannot possibly happen in a random chance alone. So it's a rare event. So it's likely to be signal. So my conclusion is their topology is different. And we have if you want to know more about the TDA, we have a workshop. Another workshop. This is mainly for the medical people, medical data. And this is actually first workshop in MICAI. And MICAI is one of the biggest medical imaging conferences. This year, there has been 3,000 paper submissions, and the acceptance was 30%. So 2,000 papers got rejected. 2,000. Yeah. And the Taekyung Lee, the former postdoc, actually wrote the first TDA paper in MICAI. So actually, I am giving a talk. Probably that's why actually. So you can do it. You can come to Zoom meeting, I guess. Now I'm always looking for the postdocs. Always.